Okay, so in the previous video we used the method of Lagrange multipliers to come up with generalized forces, and now we're going to take the idea of generalized forces and push a little further. I had mentioned in a previous video that you could either assume that F equals ma was true and derive Lagrange's equations of motion, or what we did was we assumed that Lagrange's equations of motion were true, and we saw in the last couple of videos that that gives us F equals ma. So we're going to go about and do the first bit of going with F equals ma and getting to Lagrange's equations of motion. So we'll start by thinking about what happens if you're in equilibrium. We'll assume we have n particles that are in equilibrium here. So thinking back to our lower division mechanics, we would say that the sum of the forces gotta be 0. All right. So we can take this idea of doing variations, and we can imagine that we do a virtual displacement delta Ri for each of our particles. If we do that, we can then calculate what we call the virtual work. Sum I equals 1 to n, Fi dotted with my delta Ri. And since we're at equilibrium, that would be 0. So this is actually, if you want to take this and run with it, this is actually a way, and often engineers use it to find the equilibrium of systems. They often find it more convenient to actually calculate the virtual work on the system, demand that be 0, and solve. So this is an idea that's actually due to Bernoulli for finding an equilibrium. Now, what Dalembert did is he extended this idea. So if we start with Newton's second law, that says that Fi equals Pi dot. Again, for our I being 1 to n. So what Dalembert did, and this is going to seem cheeky, but I promise it's important, is Dalembert rewrote this as Fi minus Pi dot equals 0. All right, so I'm sure you're going to just look at that and say, so what? The dude just subtracted Pi dot from each side. But this is actually a really big deal. What Dalembert is doing is we've already seen that this subtracting Pi dot from both sides, this is just introducing inertial forces. We've already worked with this. So Dalembert is taking the perspective of saying that everybody in his framework is in equilibrium. So this has the bonus of then saying that we don't have to worry about specifying who is and is not an inertial observer, which is always the big bugaboo with Newton's second law, or Newton's laws of motion in general, is say, well, they're only true for inertial observers. And it's like, no, we can make everybody an inertial observer. It'll be at the cost of inserting fictitious forces, but to the observer, they don't seem that fictitious, right? The observer views them as actual forces that are actually happening on them. You take that curve at high speed and you feel the centrifugal force trying to throw you out, right? How does that say that that's not a real experience? So anyway, Einstein took this idea and ran with it and developed a general relativity from it. But now the advantage of this is by doing this, by saying everybody's in equilibrium as long as we insert enough inertial forces into the problem. So we can go back to Bernoulli's idea and we can go ahead and calculate the virtual work for just for anybody. So let's look at one particle in 3D just to make it somewhat straightforward. So the virtual work, we'll be doing exactly the same thing. In Dalembert's framework, here are the forces acting on this particle. You've got what we would call the external forces, and then you have the inertial forces, which we would call fictitious, but the particle would say are not fictitious. And then we'll go ahead and dot that into our virtual displacement dr, or delta r. And because to the particle it's in equilibrium, it would demand that the virtual work be 0. Awesome. So let's go ahead and evaluate that dot product. So we'll be bringing back some summation notation. So this will be sum I equals 1 to 3. And that's the first and last time I'm going to write the equals 1 to 3. Fi minus pi dot without vector signs, delta xi equals 0. All right, so let's distribute this across and look at what we got. So we now have sum over I fi delta xi minus sum over I pi dot delta xi equals 0. All right. Now, from what we've done before, all right, so we'll call this term 1 here. This will be term 2. So from what we've done before, we can take our term 1, right, sum over I fi delta xi, and we can say that that is going to be sum over j sum over I fi partial xi partial qj, so now we're switching to generalized coordinates, times a virtual displacement in the generalized coordinate. So we will define, and eventually we can show that the definition is equivalent. We will define a generalized force. Qj, we'll define that to be sum over I fi partial xi partial qj. And this could be either a force or a torque. All right. We'll eventually show that that's the same generalized force that we've seen before. For now, just take my word for it that that's the punchline. All right, so with that, let's go and take a look at the second term and see what we can dig out from that. So we've got a sum over I pi dot partial, displacement xi. So what's that going to be? Well, pi is just mx dot, right? So this will be sum over I m. It's just one particle, so I don't. Yeah, I can just write mxi double dot with our virtual displacement delta xi. All right. And again, transforming this into our generalized coordinates, this will become a sum over j, sum over I, mxi double dot, partial xi, partial qj. And now our virtual displacement will be in Qj. All right. So we can break that apart a little further. So this will become sum over j. Let's put the virtual displacement out front, because that's not going to be the big deal here at the moment. Sum over I of m. All right, so we have a expanding this through a little more. We can go back and say this is ddt of xi dot partial xi dot, or sorry, partial xi partial qj minus xi dot ddt partial xi partial qj. Okay, so that was just rewriting this as being this total derivative. Now we had to throw in a correction to get that back out. All right, so we have two sums. Let's call this one 2a, and then this is a sum here, but I don't want to drag all the way over the sum sign. We'll call that 2b, and we'll look at those terms in turn in just a bit. All right. First, though, let's go ahead and take a coordinate transformation. So we can write our xi as being a sum over j partial xi partial qj j. All right. And let's differentiate that with respect to time so we can figure out what to do with my xi dot here. So xi dot will be sum over j partial xi partial qj qi dot plus sum over j of ddt of partial xi partial qj qj. All right, well this second bit here goes to 0 because of lack of explicit time dependence. Yeah. All right, so what we're left with then is sum over j partial xi dot partial qj dot would be equal to sum over j partial xi partial qj dot, and then we can cancel. So we came up with this before, but just by way of reminder, just like when we did this with the least action principle, we end up with partial xi dot partial qj is equal to partial xi partial qj. Excellent. All right, so now let's go take a look at that 2a term here. All right, so that was, whoops, make it red, black rather. That was sum over I m ddt of xi dot partial xi partial qj. And with this relation that we had before, oops, qj dot there, that'll be equals sum over I m ddt of xi dot partial xi dot partial qj dot. All right, so we can write that a little further as ddt of, this is what you would get if you differentiated with respect to your qj dot, the sum over I of 1/2 m x I dot squared. Yay! So we recognize that this is d dt of partial t partial qj dot. Okay, hold that thought. All right. Now we got to go and look at our term 2b here. So 2b becomes, well, before we get to that, so as we head into that, we just need to remember real quick that if I differentiate some function of qj and time, that's going to be sum over k partial f partial qk dqk dt plus partial f partial t. And we can clean that up just a little bit, really just notationally. I can say that's sum over k partial f partial qk qk dot plus partial f partial t. Sorry, that's as good as we can do. All right, so with that, we can rewrite 2b as, so it was sum over I m xi dot ddt of partial xi partial qj. All right. So applying this identity here to that partial derivative, we'll have sum over I m xi dot sum over k partial squared xi partial qk partial qj times qk dot plus partial squared xi partial qj partial t. All right. So I can look at all this though, and I recognize it as being sum over I m xi dot of sum over k partial partial qj of partial xi partial t. So that's going to be equals sum over I m xi dot partial xi dot partial qj. All right, so now I can look at that, and that's looking a little familiar. That's going to be partial partial qj of sum over I 1/2 m xi dot squared. So that's partial t partial qj. Yeah. So combining those two results is worth the drive. My term 2 now becomes, so that was sum over I pi dot times the virtual displacement xi will be equals sum over j of d dt of partial t partial qj dot minus partial t partial qj times my virtual displacement. Whew. So now that I got that all out of my system, I can finally put it all back together. You're probably forgetting what the it was, so we'll go back here. This is the it. So we finally got this. Now we're going to focus on this for just a bit. All right, so we now have my sum over I fi minus pi dot times the virtual displacement delta xi will be equal to sum over j d dt of partial t partial qj dot minus partial t partial qj, oops, j times my virtual displacement in qj. All right. Oops, I dropped a term. My bad. Kind of important one. This is just the pi dot part. This bit here, my fi, is going to become, my fi delta xi, we've already worked out from before, is going to be my my generalized force times my virtual displacement, the generalized coordinate. So anyway, Dalembert says that has to be 0. Now, because this is all independent here, each term has to vanish individually. All right, so we can pull it out of the sum and just plain demand that the generalized force qj minus d dt of partial t partial qj dot minus partial t partial qj equals 0. Alrighty. But we remember what this is, right? We'd already worked that out. This is going to be related to the potential. So let's go ahead and transform it into our generalized coordinates. So this will be minus the sum over I, partial v partial xi partial qj, right? And we would have had a virtual displacement there to get the rest of it to work out. Okay, so minus the stuff in the brackets is still 0, right? Well, that's all good. So we're left with minus partial v partial qj, once we do that sum, minus d dt of partial t partial qj dot minus partial t partial qj equals 0. All right. So we got a minus is a plus. So let's just go ahead and bring that through over here. So this is going to become a partial of t minus v. This is starting to look more familiar. Partial qj. So we've got my first Lagrangian there. Minus d dt of partial t partial qj dot equals 0. So I want to pause right here and say this is nice and general, super general. If you've got horrifying things like potentials that depend on velocities and stuff like that, or if your potential somehow depends on time, you're good. That this form always works. Now, if our forces are conservative, so if v is just a function of x, y, and z only, then we can rewrite this by just putting in a minus v there for free, right? Because I differentiate with respect to the qj dots, and I'm good. So this is super general, but if we've got a well-behaved potential, I can rewrite this as partial t minus v partial qj minus d dt of partial t minus v partial qj dot equals 0. And so then after all of that, I finally get Lagrange's equations of motion, having started from Newton's second law, partial L partial Qi minus d dt of partial L partial Qi dot equals 0. So it's an if and only if. Assume one, you get the other. All right. In the next video segment, we'll be taking a look at the Hamiltonian function and Hamilton's equations of motion. Spoiler alert, for classical mechanics problems, it's super hard to find any problem where it would be more useful than Lagrangian mechanics, but is very worth exploring for a couple of reasons. One, will again be touching back on Nether's theorem and what conservation laws we have if time is missing in the Lagrangian. And two, it turns out that if you have basically a zillion degrees of freedom, or like one, Hamiltonian mechanics is really super useful, and so thermodynamics and quantum mechanics both really love it. So it's good to get an exposure here. Okay, so see you in the next video.